Welcome to the second part of my discussion of conservation laws and Noether's theorem. In this video, I'll go into the origins of conservation laws in general using Noether's theorem, and I'll be building on ideas I developed in the first episode, so I'd recommend you watch that before this video. At the end of last video, I stated Noether's theorem as the following. Every continuous symmetry of the action has a corresponding conserved quantity, but this raises two key questions. What does it mean to be a continuous symmetry of the action, and what is this conserved quantity? You may have an idea as to what a symmetry is, but I'll aim to create a more mathematically precise definition to make sense of this idea. Let's consider a smooth map Q, which maps a curve Q to another curve Q star. We say Q is a symmetry of the action if, for all curves Q, and all star and n times, the action of Q star equals the action of Q. Now consider a one-parameter family of such maps, that is, a continuous set of maps, which depend on a parameter s. And when s is 0, this leaves our curve unchanged. Q is a continuous symmetry of the action if every member of such a one-parameter family is a symmetry of the action. With this definition, we can make an improved version of the statement of Noether's theorem. If there exists a one-parameter family of symmetries of the action, then any solution of the Euler-Lagrange equation has a conserved quantity. Now we've clearly stated what it means to be a symmetry, let's try and prove Noether's theorem. Let's consider the difference between Q star and Q, which can be written in terms of our map, and expanded using Taylor's theorem. We can now write Q star in terms of our original curve Q. From here on out we'll take s to be very small, so our second order terms can be neglected. Hence Q star becomes the following. Recall, if Q is a continuous symmetry of the action, then the action of Q star will equal the action of Q, so their difference is 0. We can use a definition of the action to produce the following integral. Let's now replace Q star with the relation we found before in terms of Q, and note that since s is assumed to be very small, we have the Lagrangian of a small variation in Q minus the Lagrangian of Q, perfect for applying Taylor's theorem again, this time in multiple variables. We can once again neglect the higher order terms of order s squared, which we have already taken to be essentially 0. We can now move this term inside the time derivative if we subtract off what we would get from the product rule. Now notice this term is exactly the Euler-Lagrange equation, which for any curve Q that represents a physical system must be 0. Now we have an integral of a time derivative. These cancel each other out by the fundamental theorem of calculus to give us this expression. Since we assumed this quantity was 0 for any time interval, this quantity must be invariant under time, so it's a conserved quantity, and Noether's theorem holds. Let's now apply this to a physical system. Let's consider a system of n particles, x1, x2, and so on. Our curve Q will now contain the paths of all n particles in our system. We will also assume that our Lagrangian does not depend on the positions of the particles, but instead depend on the differences in any two particles' position. This is applicable to our observations of nature. Consider a force like gravity, which is given by Newton's law of gravitation. The only reference to position here is r, the distance between the two bodies. Now let our map Q take each particle's position to xi plus sa for an arbitrary vector a. This has the effect of translating our system in the a direction, by a distance depending on s. Clearly this will have no effect on the relative distances between any two particles, as they both get shifted by the same amount, sa. Since our Lagrangian only depends on these distances, our Lagrangian is unchanged on the Q. This means the action must also be unchanged on the Q, so Noether's theorem applies. But what is the conserved quantity? Well, dqi by ds at s equals 0 is just the vector a, so it reduces to this vector expression. But what are these terms? If the only term in L depending on xi dot is the kinetic energy, then this becomes mxi dot, the momentum of the particle I, so this sum is just the total momentum of the system. Since our vector A was arbitrary, this tells us the sum of the particle's momentum must indeed be conserved. This tells us another beautiful fact about nature. Translational symmetry in space provides us with conservation of momentum. Recall how translational symmetry in time gave us conservation of energy in the previous video. Is this result hinting at a deeper connection between energy and momentum? The answer is yes. Once you introduce Einstein's theory of special relativity, energy and momentum behave exactly as space and time does in this beautiful theory. But this is a topic I'll explore more deeply in another video. Thank you for watching this video, and I hope you enjoyed. If you made it to the end, please consider subscribing for more content on maths and physics, and leave a like too. I plan on releasing a poll after this video about what topic I should cover next, so look out for that if you want to see more.